in Chapter 6, we are taking a look at, in 6.1 in particular, area bounded between two curves. So in Chapter 5, we learned about the integral, and we learned that that was the area bounded between one curve and the x-axis, which meant that the area could be positive or it could be negative. Now when we take a look at the area bounded between two curves, one important change is that area is always going to be positive based on how we set the integral up. So a quick refresher on a Chapter 5 problem here. Find the area below the curve on the given interval. So if we're given just x squared from 3 to 5, that's simply setting up the integral from 3 to 5 of x squared dx. So everything in Chapter 6 you're going to be allowed to use Math 9 for, meaning you're allowed to use your calculator. The focus is, can you set it up correctly? So if it was a non-calculator question, I would really just say, okay, what's the integral that would represent this area, this volume, etc.? And then if it were calc active, then you would be finding me the full answer. In this case, this is an easy one, a quick refresher on anti-deriving. This would give me x cubed over 3 from 3 to 5. And then I would evaluate it at 5 cubed over 3 minus 3 cubed over 3. So that would just be 125 minus 27 over 3, or 98 thirds. Right? When we do graphically the area under the curve, we're really just looking at that region right there, which there will be times that you're just going to erase everything else and focus just on the region that you're looking at. Because as we move through this chapter, we're taking that region and we're turning that region into third dimension. So we're looking at cross sections of different shapes. We'll talk about that at the end of class when I summarize. We're looking at a rotation. We're going to look at a volume in sections 2 and 3. So today, our job is just to set up that space right there, that two-dimensional space flat on your page or your calculator. So in terms of having two functions, this is what we're looking at. We are trying to find this result right here. And in order to get there, we are able to use this idea almost like we use with adjacent integrals. Similar idea. We're looking at what's the whole space, what's the area under all of f, and if I take away the area under g, that would leave me with the area between. Okay? So mathematically represented, I could write this out as the integral from a to b of f of x dx, and then I could take away the area, the integral from a to b, g of x dx, and that would equal exactly what we want. And we don't have to do it in separate integrals. F of x minus g of x dx. This is what we're going with. When I look at a space like this, to help me kind of wrap my head around exactly what I'm looking for, I box it in. And I say to myself, all right, what is containing it on the top? What is containing it down below? What's containing it left and right? So the regions aren't necessarily rectangles, but I have this mentality of box it in. I need all 4 of those parameters every time I set up an integral. When I'm integrating with respect to x, my upper and my lower parameters are the functions. The left and the right are the numbers, are the limits of integration. So in word form, I can always describe this integral as left number to right number, top function minus bottom function. That would be in terms of dx. So all of these things, left, right, top, and bottom, are always going to be taken care of. Okay. So the next page is going to say exactly this. So I'm going to skip over it. And zoom in to our first example. Okay, let me touch up this graph. The screen capture didn't quite do it justice. So the question says, find the area of the region between the graphs of the functions f of x equals x squared minus 4x plus 10, g of x equals 4x minus x squared from 1 to 3. Sometimes the problems will be laid out exactly like this. Two functions, endpoint and a beginning point, right? An interval, a closed interval, and we're able to just set up our integral. Sometimes the graph is even provided, which can be really, really helpful. But ultimately, you always want to get this graph. You want to get a rough picture in your head. You have to figure out which function is on top, which function is on the bottom. And what I mean by that, if you pick any x value along the way, where is the larger y value? Which one has the taller height? Right? So at 2, for example, red is clearly above blue. At 1.5, for example, red in terms of a y coordinate is bigger than blue in terms of a y coordinate. So that clearly defines red as my top function, blue as my bottom function. Okay? So when I set up my integral, as long as the problem or you personally define the functions with names like f and g, you're allowed to, even on the AP exam, write your integral like this. F is the top, so f of x minus g of x. That's completely acceptable. Obviously, I'm not done, but if that's the work I show, setting up my integral, that would be considered complete. For this level, I would say continue. You'll see as we move through this chapter, the level of difficulty will obviously get more challenging than this. But for now, since I still have to go to my calculator, I'd rather fill this in, being very cautious with my parentheses. And I'm going to actually simplify, because I do have like terms in these two functions. So I can say x squared minus negative x squared would be a positive 2x squared. Negative 4x minus 4x is negative 8x plus a 10. So now I have my single integral without a whole bunch of extra parentheses that I can enter in my calculator. So I want everybody to practice. Remember, it's Math 9. And I want to get our decimal, well, our answers. They're not always going to come out as decimals. They can be integers as well. Make sure you let me know if you have any questions on how to enter it. But you all should be coming up with an answer of 5 1/3, 5.3 repeated. AP and myself, when I care, I will let you know place value. Usually with the AP, it's 3 decimals. But sometimes they change it, and they tell you. So that represents that yellow shaded region bounded between F and G, 1 and 3. Questions on this? Okay. All right, so that's like the first level of problems in this section. Everything was clearly defined. There was one integral to find the area of, one region. Here's your second problem. Far less information. First of all, there's no graph given. There's no limits of integration given or interval given. Find the area of the region enclosed. That word right there is suggesting that these graphs intersect and fully enclose, right, left, top, bottom, this space that we're going to look for. Enclosed by the graph of f of x equals x squared plus 2, g of x equals 2x plus 5. You can absolutely go to your calculator. Just keep in mind, right, tests are timed, my tests and AP. So if you don't need to go to your calculator or you think that might slow you down, Sometimes you'd be surprised with what you can graph, just quick mental picture, all right? So this one I would encourage you to graph by hand, but again, it's okay. So my x squared plus 2, I'll sketch in red, is just a parabola. Vertex shifted up to 2. G of x, 2x plus 5, just a line. Y-intercept of 5. So it's going to intersect this parabola like that. Right now I don't know exactly where, but I will need to, but right now I'm just focusing on what does my region look like. Right, and that's it. So my next job, so that I know what my limits of integration are, will be to find these points of intersection with respect to x. I don't care what the y coordinates are. I just care about the left number and the right number, because the y's are enclosed by the top function and the bottom function. Those y's change everywhere. So if I were using my calculator, of course I could use math, calc, intersect, and find those points that way, which I would do if it was something that wasn't something I could do pencil and paper. How do I do this algebraically? How do I find those blue points, those x values, where these graphs intersect? Set them equal to each other. Perfect. X squared plus 2 equals 2x plus 5. When does this happen? Well, it's a quadratic. I'm going to move everything to one side. X squared minus 2x minus 3 is 0. Right? And then I can factor it. So I get x minus 3 and x plus 1. And I get x is 3 and negative 1, which makes pretty good sense based on my rough sketch. So those are my limits of integration. Those are the x values that box in my space. Some key things in our functions that are just quick: confirmation of top and bottom, confirmation of did I sketch it correctly. Use your y-intercepts. So when you're given a function, the constant, that c term, is your y-intercept. The constant for my line is 5. The constant for my parabola is 2. So that further confirms that, yeah, my line is above my parabola. Right? The y-intercepts clearly show that. And that also helps me confirm. And especially when I graph it and I only have one region, then I know for sure that the line G is above my parabola F, and my limits go from negative 1 until 3. So that would be adequate work. Then I could go to my calculator. I'm going to do a little bit more work just so that I can combine like terms, but you could enter it here. G is 2x plus 5 minus, I only really need parentheses around my F, so I distribute that minus sign. So then in my calculator, I would have a negative x squared plus a 2x plus a 3, integral from negative 1 until 3. Is anybody having any issues with calculators? Are we okay? I understand that we're probably not all plugging in right now, but just make sure you're confident in getting these answers by yourself. So you should get an answer of 10 2/3, 10.67, questions? Okay, so first two questions. First one said, here's my two functions, here's your interval, find the area around it, or in it. This one said, two functions, find the enclosed area. I'm going to skip over this practice problem. It's very similar to number 1, so it's something that I think we could all do at this level. I'm going to skip over that. And we're going to take a look at something like this. So sometimes one function won't be above along the entire interval. In this case, we will need to solve for an intersection point and set up a sum of integrals to find the area. So we will create adjacent integrals and add them up. So in this example, we can see that we have a region 1 and a region 2. And this graph does do a great job for us, telling us exactly where the endpoints are. Well, the endpoints were given in the problem, but as well as our points of intersection. It is significant that 5, being one of the endpoints, is also a point of intersection. That's helpful. Because they could have put 5 over here at 6, and then we would have had a third region, because then it changes. So you have to be able to say in a whole space from left to right, I have a top and I have a bottom function. If it changes roles at any moment, you need to create another integral, another region. Okay? So in region 1, I was given the interval -2 to 5 inclusive. In region 1, it begins at -2, and it goes until my point of intersection here, which the graph told me is at 1. If I wasn't sure, then I would either graph it and find them, or I would set them equal and find. And in region 1, if I were to figure out, well, what's above, what's below, it doesn't really matter that the majority of it were negative, because if you take, right, a negative height, let's call this height -6 right here on pink where my finger is. -6 minus, down here is like -13, right? -6 minus -13. That's going to go positive. It's going to go +7. Yeah. We're looking at area. That distance is a positive distance. So that is why, even if we are below, the distance between, as long as you're correctly picking top minus bottom, will go positive for us. So all area bounded between two curves will be positive. If you get a negative result, that means you need to flip your functions, most likely, or flip your limits of integration, most likely. So -2 to 1, pink, which is the parabola, which is f of x, minus the line, which is g of x, dx, plus region 2. Now in region 2, it would be the opposite, right? They intersected, they changed roles. Now the line is higher than the parabola. So now I would do g minus f. So integral from 1 until 5, g of x minus f of x, dx. Now the cool thing about adjacent integrals, right? We have two functions. I'm going to keep going and I'm going to show the work for how we do the subtraction. The terms are going to be the same. Right? For example, if I do 3 minus 7 or 7 minus 3, I'm going to get some 4. It's either positive or negative. Same idea here. When I combine terms through subtraction of these two polynomials, I'm going to get the same terms. One will be negative and one will be positive. I'm only giving you this hint for the sake of a calculator. I wouldn't suggest doing this normally. But you can technically factor out the negative and use the same integral both times, typed in. Right? You can copy and paste and apply the negative, making sure that you change your limits of integration. Because there will be times when you're really plugging away, you've got all the work done, and you're like, I'm not going to finish in time. There's a lot of shortcuts, if you are good with your calculator skills, that can be beneficial. All right. So here, if I do the f minus g, x squared is by itself, so it's positive. Negative 5x minus x would give me a negative 6x. Negative 7 minus negative 12 would give me a positive 5 dx. Plus integral from 1 to 5. Now when I do my g minus f, I don't have an x squared term, so I would start with a negative x squared because I'm subtracting f. X minus negative 5x goes to x plus 5x, or 6x. And negative 12 minus negative 7 plus 7 would be a negative 5. So yes, like I was saying, the terms are the same, but all the signs flipped. So you could factor the negative out of this one and make this a subtraction, similar, not the same, but similar to the absolute value, right? So now I'm subtracting a negative result, which would turn it back positive again, which is why it's okay to do this. I wouldn't show it pencil and paper work because it doesn't really conceptually make a ton of sense. Graphically, just for the sake of time, it helps. Okay, so when you're plugging away in your calculator, you should come up with a result of 37.67. So it's not really a coincidence that we keep on getting 0.33 or 0.67. That's because all of these problems so far have been an x squared, which means when it does get anti-derived, it gets an x cubed over 3. And that's where the third, right, the fraction of a third is coming from, a third or 2/3. So that is certainly common. Questions? Okay, here's another one. Similar, but now it's back to that language of region enclosed. So we want to make sure that we get all the spaces that are enclosed, and the graph is given. So there's actually 2 places where we are enclosed here. We need to find these points of intersection. The graph looks pretty clear, but again, we shouldn't always trust that. I trusted the last one because they actually had that dotted line bringing us right to that point of intersection. So here, if I wasn't sure, right, just like last time, I would take x cubed minus 10x and set it equal to 6x. I would take my functions, set them equal to one another. So then I'm going to get x cubed minus 16x is equal to 0. And this is factorable. I can take out an x, leaving me with x squared minus 16. So I have difference of squares. And it confirms the picture, right? It's 0 plus and minus 4. Okay. So I have my 2 regions, 1, 2, where the top and the bottom change roles halfway through. That's the significant part. Where do we break up my integral? I don't want to do negative 4 until 4. I break it up at the other point of intersection at 0. That's where top and bottom change roles. And that would always be the case at a point of intersection. Because otherwise, points of intersection always do this. Tops and bottoms change. Otherwise, they just become the same. And then there is no area between them. So there's always going to be adjacent integrals next to points of intersections. So region 1 would go from negative 4 until 0. Pink is above blue, right? The cubic is above the line. So we have x cubed, or f, minus g. Plus 0 until positive 4. Region 2, the line is above the cubic. So we have g minus f. Plenty of work. Like I said, you could go to your calculator on a problem like this if you've written all this down and just put the numerical answer after that. You don't have to do any more work, but you have to do this as a minimum. But it also, like, sometimes we say this is a bare minimum, right? And then we're like, but that's not really acceptable. This is totally acceptable and fine. You're not shortchanging anything. So it's fine if you just put that work.
that mean that this problem would never be a multiple choice?
No, it still could be, because multiple choice can be calculator active.
Okay, but then you wouldn't have to show all the work.
Oh, right. Yeah.
Okay.
Yeah, no, or the multiple choices would be correctly set up the integral.
Oh.
And I would have like four integral or 4 answers with slightly variations of this. And you should get an answer of, I have a 128. I think. Yes.
Miss Rod, I'm a little confused as to how you know it's like, whether it's like g of x minus f of x or f of x minus g of x.
Good question. So I am, in order to confirm which one is top and which one is bottom, right, because that's the order I'm putting it in, top minus bottom. Physically, I look at the graph, and I can use my pencil. I can lay my pencil down in that region, and I can say which one is touching at the top of my pencil, which one is touching at the bottom. So pink is taller than blue here, right? So pink, which is a cubic function, is my f. And blue, which is at the bottom, is the linear, is my g. Then if I take that pencil and I put it here, now blue is touching higher than pink, so blue, my line, is g minus f.
Gotcha. Okay, thank you.
Yep. It's all about heights. All right, take a moment, look at the next one. Try to figure out how many integrals we need to set up in order to take or find the area of this region. All right, at first glance, we're all like, oh, it's 1. Take a look. Any ideas?
So what you would do is you would,
Drew's going to talk here. 1 second. No, go ahead.
so you split the function in between where y equals 8x and y equals 8 over x squared that intersect, because you wanted to be finding the area between 2 lines, not just, and you can't do 3. So if you wanted to find where it intersects, you just set them equal to each other, 8x equal to 8 over x squared, and then you would get x equal to 1. And so you just split it up right there, and then you would do area in between y equals 8x and y equals x from 0 to 1.
Yep.
And then you would add the area in between 1 and 2 of y equals 8 over x squared and y equals x.
Perfect. Awesome. So we need to be able to break this up into 2 regions because currently there's 3 functions. And if we're looking at those 3 functions, which one's the top one, right? Well, over here, the blue one was on top of black, but over here, the pink was on top of black. So when did that role change? Well, it changed right where they intersected, at 1. So now, from 0 until 1, blue minus black, 8x minus x. From 1 until 2, that next point of intersection is 8 over x squared minus x. Don't have an answer for this one, so when you get it, let me know. 6. That's what last class got, 2. Nice, easy 6. This is the type of chapter when you get that nice answer, you're like, no way, it can't be that. But it happens. Okay, so one more topic and one more problem. One more question. So everything that we've been doing, we can also do with respect to the y-axis. We can find area, this is area of one curve bounded by the y-axis. So this is an equation as an x equals in terms of y. So if it's one equation, right, just like I was explaining with the warm-up, there is signed area. Now to the right of the y-axis is positive because that's where the x's are positive, and to the left is negative because that's where the x's are negative. When we're doing single equation with respect to the axis, we are technically subtracting 0. Our second equation is x equals 0 here, the y-axis. So for this region right here, we're doing blue, which is y squared minus 9, minus 0 for the heights. My delta y, my dy, is still positive. There's 3 units there. So I would get a positive area. But when I do it here, I'm going to be picking my right equation minus my left equation. So now I'm doing 0 minus y squared minus 9. And that's where the negative direction comes in. And then same argument up top for positive. Again, when I go to 2 equations, it's always going to be a positive result because I'm picking the correct order. The order that I'm picking now, if I'm looking at an equation with respect to y-axis, I'll write it on the next page for us. But instead of having, I'm still going to box in my space. I'm still thinking my 4 parameters. But now my right and left aren't numbers anymore. They are the equations. They are the graphs. Right graph minus left graph. I don't know if I'm backwards for you all or not. But right minus left from bottom number to top number. The right number is bigger than the left number, so when I do subtraction from right minus left, I would get a positive number always. The top number is bigger than the bottom number, so when I do that subtraction, I would get positive always. So in word form, I'll put it on top of this example that we're about to do. The integral will be set up, if we're doing it with respect to y, it would be bottom number, which is a y-coordinate, to top number, again, y-coordinate. Inside is right equation minus left equation, and all of the variables inside of my integral are y's. It's dy. The equations are written as x equals with respect to y. As we move through this chapter and it gets more complicated, the last step that I like to do is filling in the numbers, filling in the limits of integration. Because at the very end, after I've figured it all out in my head, I write the equations into the integral, and then I can say there's x's in my integral, or there's y's in my integral. And that tells me which axis to go to for my numbers. Okay, so this equation. The challenge, I find the biggest challenge in these problems, if the graph's not given, you can't pick up your calculator and type in x equals blah, 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 blah in terms of y. They just don't do it for us. There's a couple cheats that you could use. You could, type it in as y equals x and turn your calculator sideways, and it kind of worked, but not always, because sometimes they're not functions and then we're missing important things. Like it just chops off half of it, for example. For example, like x equals y squared. It's really the parabola running sideways, but if I wrote it as y equals root x, you're only getting the top half. So there's certain things that you have to be cautious of, but if you typed it in as y equals x squared, you get this, and then you turn yourself and you get the sideways parabola. So there's shortcuts. But I'd rather you use clues that we know. Same thing as before when I said use your y-intercepts. Here, your constants are your x-intercepts. So h has a -1. That helps me confirm that this pink graph has to be the -1. H is also only a square, so it's a sideways parabola. So I'm good. I know which is which. Here I have a y to the 4th, cool, more turning points, and I have a +1. Blue intercepts the x-axis at positive 1. So there's some good ways to determine which one's further right and further left, and that negative 1 and positive 1 are helpful. Negative 1's obviously further left than positive 1 is. Okay? So in this problem, I have one region when I'm doing right, left, right? I can say that blue is always further to the right than pink. If I hold my pencil here and I scan the whole space, blue is always touching further to the right. If I try to do this the other way, there's going to be times when it's written this way and you try to rewrite it as y equals, then your mindset has to flip. Then I have to say top minus bottom. Is there a top function? Is there a bottom function? The same wouldn't be true, right? If I do it here, pink is on top of pink. That doesn't make sense. All right, here blue is on top of pink, but I'd have to cut it off. Like that would make it so much harder. Turn it this way, and I'm good. So there is purpose to why we would integrate with respect to one direction rather than the other. Sometimes it makes it easier. So I always have a right, I always have a left from this point, which I could solve for, but I'm going to skip that right now, to this point. So my bounds are lower to upper, -2 to 2 for my limits of integration, right to left for my equations. So my right equation is the blue one, which we confirmed was the g, the y to the 4th. My left equation is the pink one, which is the h. My limits of integration are y values, the y-axis, -2 until +2. When you're writing it on your paper, write it with y's. So I'm going to simplify this out. When you're typing it into your calculator, you may type it in with x's. It doesn't think anything differently. It's just a placeholder. And x's are easier to find on your calculator. So I have a -1/8 y to the 4th. I'm doing the subtraction. Y squared minus y squared goes away. 1 minus -1 goes to a +2 dy. So that goes in the calculator. And I don't have this answer written down either.
I got, I think, 6.4.
Yeah, I also got 6.4.
Perfect. Perfect. Thanks. Nice job. All right, so I'm going to stop the recording. That's the end of 6.1 with area between two curves, either with respect to dx or dy.